In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call.
All right, gentlemen, we are live. I hope everyone brought their ether flute and their Marinov motor. Let me hear those Marinov motors rev. Nice.
Is that the sound of electromagnetism?
Shane, why did your motor not go off? Did you not bring a Marinov motor?
I didn't know that Toby would be so good at it, so I'm glad that I didn't try at all.
No, why would I not be amazing at a Marinov motor sounds?
What the hell?
Nice. All right, boys. Let me screen share here and we'll get into it. And then Stone has an analysis of the Marinov motor, and I think a critique of this paper as well. So this is Thomas Phipps Jr. and his analysis of the Marinov motor, and I think he built one and stuff. So we'll get into all of that now. So introduction.
Yeah.
Okay.
Sorry. I was gonna ask if I could read first if we're doing popcorn.
Yes.
Perfect. Let me know when you're ready.
On you, sir.
All right. We're just above introduction. It says, it is verified that the Marinov
Oh, I
motor...
definitely think you should read the abstract. Just scroll up just a tad there, Alan. Let's start with the top.
Oh, yep. Thank you, sir.
Yeah. It is verified that the Marinov motor works and that its torque magnitude roughly agrees with the theory given by Wesley. The existence of this device appears to refute the widely held belief of physicists that the Lorentz force law suffices to describe all observable electromagnetic force manifestations. What a claim. I confess to having had the popular, among physicists, view of Stefan Marinov as a buffoon, adept primarily at self-advertising. That opinion I no longer hold, since I have been able by my own observations to confirm the operability of one of his inventions, a motor he called Siberian Kolyu. I follow Wesley in calling it here simply the Marinov motor, MM. Wesley's done a service to the physics community in clarifying, by means of a simple sketch, figure 1 of his accompanying paper, just what the Marinov invention is. Figure 1 of the present paper shows the same thing, but with sense of rotation corrected to agree with what has been observed empirically for the case in which the vertical members of the toroid are permanent magnets. It will be seen that the elements are starkly simple. A permanent magnet of roughly toroidal shape, entirely enclosing its own magnetic B-field flux, is placed inside a conducting ring. If the magnet is held stationary in the laboratory, and the ring is supported in bearings, then the ring will rotate continuously in the laboratory, providing that direct current is brought into it through sliding contacts, or brushes, situated in the vertical plane of the toroid. Alternatively, and more easily tested, if the central toroid, termed the armature, is suspended by a filament, as is in a torsion balance, so that it is free to rotate, and the ring is held fixed in the laboratory with current leads attached to it, adjacent to the vertical members of the armature, then a measurable torque will be exerted on the suspended armature when current 2I is turned on, which then divides so that current I flows in the upper half of the ring and I in the lower half. This torque, which is easily measured, causes the armature to turn up to 90 degrees. The extreme simplicity of this conception must be emphasized, and also the bizarre nature of the force which is responsible for the observed unidirectional torque. Everything is electrically neutral, so there is no E field to speak of. And magnetic flux in the case of an ideal toroid is entirely confined within the toroid. so that no B field is present at the position of the current. Hence, V cross B or I cross B should vanish. In this idealized case, the Lorentz force law would predict zero force and zero torque. Of course, in any practical realization of the concept, there must be flux leakage, but it is at least surprising that a seemingly second-order phenomenon, weak and random in character such as flux leakage, in all cases thus far investigated by at least 3 independent U.S. observers, T. Ligon, J.D. Quistra, and myself, should consistently yield strong torques. Also, if departure from ideality were driving the motor, then enhanced departure should drive it better, but it does not. The question of torque sense seems empirically to depend on construction details of the magnetic toroid. We shall not try to resolve all complexities here, but offer a simple rule of thumb. Now, referring to our figure 1 in this picture, it's a schematic of one simple form of Marinov motor. The indicated sense of ring rotation agrees with what has been observed for the case in which the vertical members of the toroid are permanent magnets, as you see there in figure 1. In figure 1, current flows clockwise, as seen from above, in the near half of the horizontal ring, and counterclockwise in the far half of the horizontal ring. The B flux is largely contained within the toroid and circulates clockwise in the view shown in figure 1. So get that, the ring, right? You would think that the ring, it would all be traveling in the same direction because it's one ring, but actually the side of the ring that's nearest to the picture is going clockwise, and the side of the ring that's furthest from the picture, it's traveling counterclockwise. So they're like going against each other, meeting at like the vertical axis of the toroid plane.
I would interject with one thing, go back to the figure. And it's something that I don't see addressed in the paper, nor do I address this in my analysis, so I figured I wanted to mention it now. That what could possibly be the mechanism, the mechanistic cause here? And it very well may be the actual resistance of the ring itself in terms of current flow. That when you come off positive, moving to the right and then up and then into the ring motor from the right, voltage there will necessarily be larger than the voltage on the opposite side of the ring when both of those two currents reconversion leave the ring, because of the nature of the material the ring is made of. That there is resistance in the ring, therefore the voltage potential is asymmetrical across the ring. It's a bit of an illusion, and that is just one of the illusions presented here that I wanted to point out. By all means, continue.
Maxwell's equations, incidentally, provide no means, without cutting into the toroid, to say which way the flux goes. But we may consider ourselves possessed of this information as a result of having constructed the toroid from magnetic parts such as bar magnets. So, since the B flux lines are contained in the toroid, and in any case they lie in a plane normal to the ring plane, why does the ring turn always one way rather than the other? A clue to handedness comes from recalling the original ampere description of a permanent magnet in terms of tiny current whorls, which in modern parlance would be aligned electron spins. If we slice horizontally across a vertical arm of the toroid at the level of the ring, in thought, we expose a planar assemblage of these current whorls, which are considered to cancel each other internally and leave uncompensated only a surface polarization or a magnetization current, which is treated in Maxwell's equations in the same way as a real current. The important thing to note is that this virtual surface current is unidirectional, and it has a definite sense determined by the sense of the flux internal to the magnet. If the flux vector points up, as it does in the left side of the toroid shown in the figure, then by the right-hand rule, the sense of circulation of the surface current in that portion of the magnet is counterclockwise, as seen from above. We treat it as a conventional plus current, as if it were real current in a solenoid. So here, finally, is something about the physics that favors one sense of torque acting in the horizontal plane over the other. But note that none of this is obvious to the eye of the beholder. We have had to ascribe a sense to flux that's not visible and a sense to surface magnetization current that's also not visible. In the older electrodynamics of Wilhelm Weber, which featured direct action at a distance of one electrical point charge on another, the magnetization current circulating around the surface of the permanent magnet nearest to the ring would presumably be treated in the same way as real charge in motion. It would induce an action on the real currents in the adjacent ring portions that would lead to exertion of a ponderomotive force on the ring. An alternative, essentially equivalent approach, employs the original Ampere force law between current elements. Although quantitative calculations using this law would be complicated, it does furnish a simple rule of thumb by which sense of rotation on the Marinov motor can generally be inferred. Adjacent, or side by side, parallel current elements mutually attract and anti-parallel elements repel. This rule also works for the Lorentz force law under the same fiction that surface magnetization or polarization currents are real ones. Applying this to components of virtual surface current and to components of real ring current in closest mutual proximity usually gives the correct sense of rotation without any need for integrations. Thus, considering the left toroid member of figure 1 with B flux up, as it's going up on the left side, the virtual surface current on the toroid adjacent to the ring is counterclockwise, so it's parallel to the far ring current and anti-parallel to the near ring current. Hence, the far part of the ring is attracted and the near part is repelled. Both these actions produce a counterclockwise rotation of the ring as is observed. Now, this is only an empirical rule. Unfortunately, it does not distinguish among the Ampere, Lorentz, and other classical force laws. For that, both further experiments and more exact theoretical calculations are needed. Wesley analyzes the situation in more modern terms of vector potential A, related to B field by B equals nabla cross A. Because of its normalization or gauge problems, this potential has been supposed, since the days of Heaviside, to be not physically real. But this is hard to accept in view of more recent evidence, such as the celebrated Aharonov-Bohm effect. Comparing with our figure 1, it will be seen that the Aharonov-Bohm experiment is just a one-solenoid version of a micro-Marinov motor, with encirclement by the two parts of a single electron playing the role of the ring current. Wesley simply defines A as the integral of current density divided by separation distance from the test element detector, thereby fixing gauge and unambiguously determining both the A vector and the B vector. Now, this seems a reasonable solution, though hardly respectful of those physical theorists who have founded gauge theory on a different definition. Ultimately, some other mathematical language will doubtless be found to describe what is happening in the Marinov motor. Meanwhile, the vector potential appears to suffice. Both Marinov and Wesley noted the sufficiency of the A vector potential. In accepted electromagnetic theory, it is established doctrine that only the E field does non-vanishing work on charge, and that E field is related to the potentials by E equals negative nabla phi minus the partial derivative of A over the partial derivative of CT. Such a formulation does not suffice to explain the observed torque in the Marinov motor, but these investigators noticed that a slight formal modification of this definition, replacing the partial time derivative with a total one, E equals negative nabla phi minus 1 over C dA over dt, introduces the convective part of the total time derivative, d dt equals del t plus v sub d times nabla, an extra dot product nabla, an extra convective force term that can be associated with motional induction. The force of convection, which is motional induction, equals negative q over c times v sub d dot product nabla times vector A, which is just right to account for the observed torque. This is true because the A vector is not confined within the magnet or solenoid structure, but describes what Wesley terms an A field existing outside the magnet and in contact with the conventional plus ring current, which has velocity v with respect to the laboratory or with respect to the magnetic source of the A potential as Wesley conceptualizes it. We consider the convection to be affected by an A field detector of velocity v sub d co-moving with the actual electronic charge carriers constituting the current. In other words, it's anti-parallel to conventional plus current, so that v sub d equals negative v. In this relation, qv equals IDS. Both v and ds point in the direction of conventional, well, he uses plus instead of positive for some reason, plus current flow. So q and I are to be treated as positive quantities. Our choice to use conventional plus current in describing the sink current is demanded by consistency with our similar choice in describing the source virtual current that determines the sign of A. The opposite choice, to consider negative electron currents at both source and sink, would change the signs of both Q and A without affecting V sub D, so that by equation 2A, the observable torque sense would not change. So he's like, you can use positive or negative, we use positive. Eliminating the C factor by suitable choice of units, we can write our new force in a form more useful for calculations, which is that. Now, this new force term, by the way, was actually tacitly employed by Dirac in formulating his electron theory, as has been pointed out elsewhere. Now, and here's where it starts to get a little interesting. As a footnote, I may add that a justification for using the total time derivative instead of the partial one in all equations of electromagnetic theory was given by me in a 1986 book. So this paper we're reading right now is from 1998. There, in the 1986 book, it was shown that Heinrich Hertz's first-order Galilean invariant reformulation of Maxwell's equations amounted to just this very replacement. A del t equals d dt, plus a trivial adjustment of the current source term to allow for Galilean velocity addition. I also pointed out that Galilean inertial transformation invariance at first order requires the same replacement to be made in the treatment of the vector potential. The convective velocity parameter v sub d was there identified as velocity with respect to the observer's inertial system of whatever detection instrument gives operational meaning to phi a. In other words, the lab where you have your detector. This fits the present case, in which the A produced by the totality of magnetization current in the armature is measured by a hypothetical instrument co-moving and co-located with a physical current-carrying point charge within the ring. That is the meaning of convection. Thus, first-order invariance demands that all time derivatives of both field quantities and potentials must be of the total rather than the partial variety. Such invariance embodies first-order quote-unquote relativity, although it violates space-time symmetry, since ddt is not mathematically symmetrical with del t or del s partial space derivatives. Now, I confess that this 1986 recognition of the need for total time derivatives was a purely theoretical observation on my part, and that I had no inkling of any practical implications for observable effects, nor of the work of Marinov or Wesley in this regard. The superiority of invariant formulations should need no selling to physicists or mathematicians. What apparently needs selling is the almost self-evident proposition that first-order force effects are the ones most plainly visible in the laboratory, and that first-order invariance requirements, which are entirely overlooked by physicists in favor of going at once to covariance based on second-order considerations, v squared over c squared Einsteinian stuff. They'd rather look at second-order Einsteinian covariance than first-order direct measurement invariance.
Ain't it the way?
But these first-order invariance requirements must be met first in order to describe properly, or in other words, in any conformity with the Galilean relativity principle, in order to describe properly all physical forces observable at first order in inertial systems. In other words, you have to satisfy first order invariance requirements in order to describe properly all physical forces that are observed. Thus, I repeat one of my litanies, that each order of approximation constitute a physics of its own, answerable to its own invariance requirements, and that first order approximations take preemptive precedence. In short, valid theory must be compatible with a development by successive orders of approximation, starting with the first. The new force that drives the Marinov motor could be called the Marinov or the Wesley force, or it could with equal justice and accuracy be called the Maxwell-Einstein first order mistake force.
Gloves are off.
That's what I'm calling it from now on. Oh, have you guys heard of the Maxwell-Einstein first order mistake force?
The mistake was in failing to demand rigorous formal invariance of the equations of electromagnetism at first order. Einstein in particular should have paid more attention to Hertz by actually trying to understand him instead of sweeping him under the carpet in the typical physicist way by reference to quote-unquote Maxwell-Hertz equations. The fact is that Maxwell's equations are space-time symmetrical, whereas Hertz's are not. Because as we said, alongside partial space derivatives, they contain total time derivatives rather than partial ones. Although Hertz's execrable non-vector notation admittedly hid this from the hasty eye. In other words, it wasn't easy to see it at first. You had to pay attention to Hertz's work. So there are no Maxwell-Hertz equations, and Einstein's Maxwell-Hertz reference was an oxymoron. But no physicist even today gets the joke, because all are as heedless of Hertz as was Einstein. To say that there is no first order invariance is to say that there is no first order relativity, and that is contrary to 19th century empirical evidence of Mascart and others who showed first order relativity to be an experimental fact. Isn't first order relativity just Galilean relativity? Because isn't everything Einsteinian second order? It's v squared over c squared ratioed.
Yeah, I was going to say, I don't even know how they could first order it. It's second order theory.
Yeah. I think first order relativity is just Galilean invariance. I think it's just like shifting your coordinate system from here to there. I don't think it has anything to do with anything Einsteinian. In this paper, we shall first apply the basic theoretical torque formula obtained by Wesley without repeating his derivation of that result. And I could be wrong about that. I have to look at Mascart more specifically, but that's what strikes me at first read. But in this paper, we shall first apply the basic theoretical torque formula obtained by Wesley without repeating his derivation of that result. The purpose will be to suggest some of the range of variations possible in the basic design of the resulting new class of motors. Then some experiments I did to test the torque formula will be described. No attempt will be made here to analyze specific embodiments of the Marinov motor, but any reader with engineering leanings will be able to fill in that part of the story.
I think that's a mistake, but let's go with it.
What, that people would be able to fill in the story if they're
Yeah,
engineers?
that he didn't make any actual comparison. You know what I mean? He just like, oh, it's like that, but we're just gonna move it along. Let's talk about formulae.
Right. We'll get there in a second, but he basically does measurements, and he's like, while these do describe pretty closely the theoretical, like quantitatively they match pretty closely, but qualitatively the curve isn't the same shape, so there might be something off here in the way we're describing it, but we do know at the very least that there is a force happening, and that's not predicted by the mainstream explanation of it. But I'm gonna popcorn to somebody.
For anybody who also has those engineering leanings, hopefully you're going to notice something rather conspicuous in the next two paragraphs.
Ooh, I was gonna say, any engineering readers out there? Our boy Man of Stone, but anyway, we got the torque formulas. For a current carrying ring radius r surrounding two oppositely orientated north and south poles up infinite length solenoids of each infinitesimal radius at and cross-section area of delta A, having centers located azimuthally on the ring of the diameter at which the current is introduced to taken out of the ring, was introduced to and taken out of the ring, at the radii plus or minus b. Wesley had derived the formula for the infinitesimal increment of the ring torque magnitude corresponding to delta A, given by equation 3. Here the links are expressed in centimeters, B sigma, BO, I don't know. The field internal to the solenoid in Gauss, I amp, is DC in amps flowing in either half of the ring, the total current in the external circuit being 2 I amp. The factor of 10 converts AB amps, ab amps into amps, yielding the torque to dyne cm. I don't know what that is.
Yeah, dyne centimeters.
Oh, thank you, sir. To convert to practical units of torque, or US units of torque, foot-pounds, multiply the torque by dyne centimeters by that ratio there. And see, the torque is assumed to the result of the ponderomotive force applied to the ring at the radius r. The geometry in plain view is sketched in figure 2a. For the purpose of our analysis, Wesley considered solenoids. In my limited experience, it is possible that real solenoids, even when contained core materials at high permeability mu, they do not perform in accordance with equation 3, may possibly do so if B is replaced by the H field.
Orsted.
Thank you, sir. There being an insufficient evidence on this subject, I leave that to speculation, to stand simply as a warning against the unthinking interchanges of the real solenoid electromagnets and permanent magnets that conclude with the remark that the empirical evidence on rotation and sense in regards to the armatures made for the combinations of the permanent magnets and magnetizable iron can be summed up in the rule of thumb stated in induction. However, this rule must be applied exclusively to the permanent magnet portions of the magnet circuit, the toroid. Any portions that contain only externally induced flux can apparently be ignored. In the situation not unlike that for railguns, must be considered presently unsatisfactory and in need of further investigation and clarification. If the ring is fixed, the torque in the inner structure, the solenoids, magnets, considered rigidly connected, and in the opposite sense of the sense on that ring, in equation 3 must be modified vis-a-vis multiplied by B over R to account for the smaller radius of the force application. It is force, not torques that obey Newton's third law. We obtain a more revealing form of the torque formula by letting B equal R minus delta R, where delta R will be considered much smaller than R. And that's equation 3 can be written by equation 4. This form shows the important. Did you want to say something? I thought I heard someone's mic cue up. My bad. Okay, this form shows the importance of the proximity of the solenoid to the ring. At first order, torque is inversely proportional to the separation distance delta R. The parameter appearing here is CB I amp over 10 pi. The combination shows the equivalent torque improvement to the result proportional increase of either BO or B amp or I amp. Observe the formula in equation 3 is symmetrical to B and R except in the sign change. This means that if we cancel the sign change in the interchanging north and south poles of the solenoid, we could place the flux reversed solenoids outside the ring in the configuration shown in 2B and use the interchange formula given by equation 5, where B prime formally replaces B, for a symmetrical superposition of the two cases just considered illustrated in figure 2C, letting B equal R minus delta R. As before, B prime equals R plus delta R. We obtain, by adding the separate torques, the total torque given by equation 6. In adding to doubling the torque or twice as many solenoids, it will be observed that the departure from 1 over delta R behavior in 6 occurs at the second order rather than the first, as in equation 4. This results from a higher order of symmetry in figure 2C as compared from figure 2AB. Since Wesley's Gadankin solenoid, since Wesley's Gadankin,
That would be Gedanken.
Gedanken, thank you. That means thought experiment, right? That's not like a real thing. Since his thought experiment, solenoids extend vertically to plus or minus infinity. Oh, dude, the old plus or minus infinity. Hell yeah, brother. We can imagine that the connections interchanged at infinity. So that is what is portrayed in figure 2C. May be interpreted as a pair of two magnet toroids, each obtained, e.g., by clinging together with elongated U-shaped magnets, one circling the upper portion of the ring shown in the figure, and that the other encircling the lower. Because of the importance of the proximity considerations already noted to what happens near infinity, it is not important. And in that fact of the vertical extension of the magnets represented by the solenoid, judging from empirical evidence, can be safely curtailed. Although no theoretical attempt is made here to quantify the penalty for vertical truncation of magnets. This is done elsewhere in citation 12. We'll take a quick gander here at this figure 3. So this is a variant of figure 2a in which the magnet armature vertical plane is inclined at the azimuth angle phi.
Psi.
Oh, psi. To the ring diameter containing current leads to the ring motor.
So hold on. What he's actually showing there is that there's an orientational change between the places on the ring where the current enters at A and exits at E, and the north and south poles, or I guess the north and south polarities of the magnets themselves coming in and out of the page relative to that plane, that they are already torqued away by angle psi, which you can see just between the segments AO. The two of them are drawn on the inside diameter near the center, that there's one on either side of the north there, those two little guys. Exactly. Yep. That's the value that he's talking about right there, that there's an offset, and that's essentially creating the asymmetry by which we would derive the torque.
Thank you, sir. In summary of what we have learned, so far, proximity conduces to maximum torque, and placement of the extra magnets or solenoids in close proximity to the ring can enhance torque. Similarly, it is easily shown that the placing of extra rings in the vertical stack above one another will proportionally enhance torque, all other things being equal. Similarly, wiring half rings in a series can be done in such a way, as shown in citation 12 and 14, as to double the torque. As such means that it is anticipate. What's up?
I doubt that in practical, but we'll preserve the illusion for now.
Yeah, we'll come back to that one. Big claim. By such means, it is anticipated that the performance comparable to the existing motor types may possibly be obtainable in the citation 12. Analysis for arbitrary magnet cross-section shapes. By integrating the formula 2b, Wesley obtains a formula in 1 that can be written apart from the differences of signs shown in equation 7a. For force of one quadrant of the ring that includes a range of azimuthal angles of phi between 0 and pi over 2 exerted by a potential produced by the virtual surface currents flowing to the solenoids at all angles in radians.
I'm sorry, Alan, this pi over 2, that's the 90 degrees he was talking about in radians.
Gotcha. And so here Wesley shows in 7b what Stone was just talking. The signs of the current for the 4 quadrants being favorable to the force reinforcements he gets for the case of the 4 quadrants, a result of 4 times greater given by equation 8. For a total azimuthal force of the ring produced by the action of the solenoid in the A vector potential and the geometry of figure A2 or 2A. We multiply by the torque arm R, and it yields, since A phi 0 equals 0, the torque formula from equation 3 above. We set the old sand crabs.
Yeah, that's exactly where they would be, quote unquote, parallel with each other from the entrance and exit points of the current to the ring, where the north and south would be aligned with that at what they call 0 degrees. That's what's in parentheses in that square bracket expression.
Thank you, sir. Oh, so it's like signifying that where the starting angle is or whatever.
Yeah, that's the vector A potential at 0 degrees moving towards 90, and they're applying the difference there.
All right, we need to consider the more general case of arbitrary azimuthal offsets angle psi in order to assess the contributions of the force of the ring of the pair oppositely oriented solenoids, such that one is located at an arbitrary position B psi, and the other symmetrically across from the opposite quadrant of B psi plus pi, psi pi. Some would say. All right, and then we'll take a look here at this diagram here. So we got figure 4a, the variant of figure 2a, in which the armature magnets of opposite polarity have infinite cross-section areas, A0, of arbitrary shape, B or A naught. B, detail of the pole cross-section of A naught showing the hypothetical Amperian current loops that cancel internally to produce the virtual surface current circulating counterclockwise for the North Pole as seen from above. Each loop may be considered to enclose the B flux line. Conventional plus current is assumed. Any comments on this diagram?
I assume he's talking about north coming out of the page, and I addressed this in very briefly in my review too.
Nice. Did you record a video for that, or are you just going to do it live?
No, it's just something I did in the 3 hours before we got happening tonight. I've got it down on page.
Nice. Cool. Okay, let's see. Where do we leave off at? I think it was right here. Wesley's results is easily generalized to handle this. The geometry in question, sketched in figure 3, the case where B is greater than R, is treated. Is less than R. We consider the ring current to be led in a point at A and out of E. Okay, offsets by the azimuthal angle psi is the line BF on which lies center of the infinitesimal solenoids at each radial distance B from the center point O. For analysis, we construct the line CG offset by the same angle psi on the other side of the inner solenoid line. By a roughly qualitative consideration involving the directions of the current flow in the ring versus the surface current flow on the closest part of the adjacent solenoid, applying Ampere's rule for the sense of rotation, it is easily seen that the force on the ring is clockwise in figure 3. Along the arcs of BC and FG, and counterclockwise along the arcs AB and EF. Counterclockwise. Moreover, it is clear from the symmetry about the lines of BF that the force on BC cancels the force on AB. Likewise, the force EF cancels the force on FG. But we can forget about the arcs AC and EG and just concern ourselves with the remaining arcs EC and AG. Referring to Wesley's geometry in figure 2, we see that the arc BD in figure 3 corresponds to the quadrant he analyzed. So all we have to do is take 4 times the result of integrating over the arc CD. Wesley defines his general azimuth angle phi as increasing counterclockwise from the azimuth line. OD on the normal to OD the normal to the inner solenoid line. Thus, the integral over the arc CD goes from phi 0 to phi equals pi over 2 minus psi, so that this is for the quadrant, given by equation 9a. The minus sign results from the fact that the currents are represented in figure 3 show a clockwise long arc CD oppositely to the direction of positive increases to phi. Hence, the net ring on the torque is negative or clockwise. As Wesley's case in equation 8, the result from the 4 quadrants is easily shown to be 4 times the single quadrant value given by equation B. In going from the force to torque, the same care can be taken. The torque on the ring as a rotor is not just a negative, is not just the negative of the torque on the solenoids as the rotor, for the reasons that Newton's third law, as previously noted, does not apply to torques. Let us address the first, the case of the torque ring as a rotor. Since the sine of pi over 2 minus psi equals the cosine of phi, or psi, equations 7b and 9 yield the total force on the ring. And here we got another diagram if you want to take any comments on that. We got figure 5 is the variant of 4a, in which the magnets have parentheses cross-shape sections. And then we have equation 10 here. Very nice equation. I like these brackets myself. Anytime you can get these brackets in an equation, that's always a positive in my book. We can forget about the signs at the and treat I amp as signless. If we deduce rotation sense by the ampere rule previously stated, the ring torque is simply delta T ring of phi. What's up?
Hi.
Or psi, sorry. Or someone's talking to their
doing?
dog.
Oh, my bad.
Yeah.
Oh, shit, dude.
It's all good. Equals R delta F sub phi of psi. Nice. Phi of psi. Suppose our stator consists of a pair of magnets of arbitrarily shaped cross sections indicated by a region designated A0 in figure 4a. A magnet of opposite polarity and of shape of the mirror image of A0 by reflection of the point or of the origin point at the center of the surrounding ring is presumed to be present. We ask what torque is exerted by the fixed magnet on the pair of rings. To answer this, we only have to integrate the incremental torque contributions from each of Wesley's infinitesimal solenoids over the whole area of A0, whatever the shape is. For figure 4b shows by the original amperes construction of the small solenoids, currents cancel the interior region of A0 and leave only the surface current circulating on the boundary of the region. It is this virtual surface current that we have been considering to act on the ring via its vector potential, but by linear superposition, the torque action of the infinitesimal solenoid can equally be calculated by the addition integration, by simple addition, just integration. The shape of the infinitesimal areas being inconsequential, we shall suppose that the delta A equals BD psi, a form adapted to the polar coordinates relative to the center of the ring. Then the total torque on the ring rotor due to the magnets of an arbitrary shape of A0 is given by equation 11, where T ring equals all that. Very cool. Where F of RB psi is the function given in equation 10. By contrast, if the ring is held fixed in the lab in the inner permanent magnet rigid structure, having an arbitrary shape of A0 together with its image magnet of opposite polarity is the rotor, then the torque of the magnet, rotor, or motor armature is the sum of the individual torques for the solenoid situated at various B values visa equation 12. We have a graph here, very nice. Figure 6 calculated the values, normalized integrals for the case of the ring rotor and the ring stator. For the variable clearance parameter, very nice. Any comments?
I don't particularly agree with this interchange as a
Not feeling it?
premise. Yeah, but again, we'll preserve the illusion. Let's roll with it.
All right, we're preserving. All right. Let's see. We are fortunate in both cases, 11 and 12, that the integrals can be evaluated in closed form for sufficiently simple boundary shape of A0. Thus, if the parentheses shaped magnets shown in the Magnets of short shown in figure 5 are employed the integral of equation 12 over the half of the area A naught of one of the members of the symmetrical pair of the oppositely orientated magnets in the ring stator case takes the form of equation 13, where psi is half of the angle that either magnets subtends to the center of the ring and that the material extends radially from C to D. Here, psi is in radians and CD is in centimeters. It happens that the double integrals of both equations 11 and 13 can be evaluated exactly. Note that equation 11 refers to the case of a stationary magnet and rotor, whereas equations 12 and 13 refer to the case of a rotating ring and stator. In the latter case, the total torque on all magnets in the latter case, the total torque on all magnet portions is simply twice the above result. Expressed in foot-pounds, this is equation 14. Here, CB equals 0.4B naught I amps over pi, where B naught in Gauss and I amp is the magnitude of the DC amperes flowing in each half of the ring stator.
You guys all seeing the arithmetic sleight of hand in equation 14 tacked onto the end? That's all I'm saying for now.
Let's take a gander here. We looking at some light speed?
Nope, but that's a good guess.
Nice. All right. Let's see. What's the sleight of hand? Do you want to give us the gravy, or is it at the end?
Yeah, it's about unit of measurement, that he's still in amps and Gauss, but he's not in foot-pounds, and that's why that coefficient is on the end.
That is he the bad man, or what does that mean?
I'll cover it after. Let's go.
Oh,
It's some of the surprise, I guess.
Okay, cool. All right, let's see. The double integral I in equation 13 or its counterparts with the integration from 0 to psi in equation 11 is readily evaluated by any of the several computer algebra programs, but the expressions are too long to reproduce here. Dang, when it's too long to put in your 16-page paper. Porch. See. I used and highly recommend the user-friendly program Derive. Ooh, Shane, how about that, dude? You ever heard of that? Putting in various numerical values to explore the parameter sensitivity, we find the following qualitative results. 1. There is considerable sensitivity to the magnet outer radius D, which should be near R as feasible, or which should be as near as R as feasible. The difference in R minus D represents the clearance between the rotor and stator, which is advantageously small. Figure 6 shows the value of the integral I in equation 13 as a function of D, where R equals 20 centimeters and P equals 45 degrees expressed in radians always, but we omit further mention of that. Okay. C equals 8 centimeters. The figure is drawn to show that both cases discussed above, the stationary case of equation 12 and 13, the lower curve open stars, and the stationary magnet of equation 11, the upper curve of the shaded circles, the difference is seen to be about 25% or more in favor of the ring rotor case. And here we go with a figure 8. The same as figure 6, the variable azimuthal angular half width of the magnet P. And here we are with our stars and circles. Cool. The reason that this much of torque in the ring stator case is exerted insufficiently on the magnet portions at small radii, small torque lever arm. 2. The torque is rather insensitive of the value of C, which determines the magnet width D minus C at the smaller values of C, but falls off drastically if the magnet is made too narrow in the case of increasing C beyond about 10 centimeters, as shown in figure 7. That figure assumes that R equals 20 centimeters and P equals 45 degrees and D equals 19 centimeters for the other parameters. Okay. This is a wide range. This is rather wide, 1 centimeter gap Decreasing it does not alter the qualitative comparison of the ring rotor and the ring stator, cases shown with the same meanings of the stars and circles in Figure 6. The significance of the magnet azimuthal limit P is indicated in Figure 8. This shows for a radius equal to 20 centimeters and D equals to 20 centimeters, the effect of P variation on the two cases, the ring and the stator, or the ring rotor and the ring stator. The other parameter of the value assumed in the figure is C equals 8 centimeters. Evidently, subtended half angles in excess of 45 to 50 degrees yield comparatively little torque improvements, but decrease below at about 50 degrees, or 30 degrees are costly. Nice. All the results presume infinite length magnets or solenoids. Formulas describing the effect of the magnets truncated are given elsewhere in citation 12. So much for the overview of the theoretical side. We turn now to the matter of the empirical verification. The torsion balance.
Goody.
Yeah, the good part, right? The torsion balance measurements of torque. The writer is not the first observer in this country to confirm the existence of non-zero torque in the Marinov motor. As reported by Kustera, Ligon, and was the first to recognize that an easy way to test this concept was to suspend the toroidal magnet armature shaped somewhat in Figure 1 of Wesley's report within the horizontal copper ring fixed in the lab to which currents leads are attached. This eliminates the need for brushes and emulates one of the practical brushless motor designs, which, however, requires periodic DC polarity reversal. Ligon observes vigorous turning of the armature up to almost 90 degrees when when strong DC current was put through the ring. At 90 degrees, there was a torque null, and beyond that, a counter torque. The approach reported here was patterned by Ligon's. Is that his name? Am I saying that right? It's bothering me.
Ligons? I don't know, man. Ligon? I don't know how far
yeah.
you want to go with that.
That's far enough. As long as you don't know either, I'm good. So it's Ligon's now. In order to make the semi-quantitative measurement, I used a torsion balance sketched in Figure 9, wherein the horizontal wheel is in 2-degree increments around the rim, mounted at the vertical shaft, held in bearings, could be rotated. Ooh, very cool. Here's our schematic for Figure 9, the schematic of the torsion balance used presently, reported torque measurement. And here's the balance of the calibration method. Very cool. Though the measured azimuthal angles to compensate for any torque applied to the suspension fiber coaxial with the shaft, thus by twisting the wheel of the armature could be returned to its initial azimuth by the null method. This was judged by observing the return to a fiducial position about 10 feet away. Way of a diode laser spot reflected for a small mirror, not shown affixed to the armature. After some false starts, the suitable suspension fiber was found at about 5 inches length of 0.005 inch, 127 micron diameter tungsten wire. The ring was a copper gasket of a thickness of about 0.21 centimeters, the conductor width of about 0.6 centimeters, and the mean radius of R equals 2.118 centimeters. To which heavy leads of insulated number 12 stranded copper wire were soldered at opposite ends of the diameter. This leads straight out horizontally of each side of about 15 centimeters. The lead dressing was not to have found to have any appreciable effects. The armature suspended centrally within the ring consisted of 2 oppositely orientated vertical Alnico cylinder magnets, each 5 inches long and 3/8 of an inch in diameter. The bridge at the top and by the bottom, or bridged at the top and the bottom by small rectangular pieces of soft iron. The vertical members were aligned in the vertical plane containing the ring diameter where the current was led in and out, like the configuration shown in Figure 1, but with the reverse current direction. The separation of the two centers of the two-cylinder magnets was about 2.38 centimeters. Hence, the magnet radius parameter B had a value of 1.19 centimeters. This implied a clearance parameter of delta R equals R minus B equals 0.928 centimeters, which is quite large, i.e. unfavorable to high torque. Measurements with the AML GM1 Gauss meter using the Hall effect transverse probe of about 1 millimeter thickness inserted between the two of the cylinder magnets indicated an internal magnetic field of about V naught equals 2,300 Gausses. Is that a lot of Gausses or what?
Yeah, that's a fair bit.
Nice. All right, here we go. See, the current was provided by the Hewlett-Packard 100 amp DC power supply. Shout out to the boys. The model Harrison 260 or 6260A. The values of the ring current I amp up to 10 amps, 20 amps in the external circuit were used. For small angles approximately linear, dependence on the current ring or of the current wheel angle delta theta obs required to compensate for the torque of the armature was observed. The findings can be summed up in the empirical formula given by equation 15, with an average of about 10.5 degrees of fiber twist per ampere of DC current flowing in each side of the ring. To quantify this term of torque, we must discuss the calibration of the torque balance. Second. All right. This will probably bring smiles to the faces of real, i.e., government-funded physicists. Oh yeah? But the truth... Hang on a second. All right, let's see. This will probably bring smiles to the faces of real, i.e., government-funded physicists, but truth will out. The balance was calibrated by the peasant's own method, shown in Figure 10. A cotton thread was attached to a fixed horizontal micrometer slide. To the lower end of this thread was tied to a known mass of M equals 10 grams. The thread contacted the horizontal plastic drinking straw, the thread contacted a horizontal plastic drinking straw, light, rigid, high-tech. What is this?
Epoxied, glued.
Epoxied. Yeah, thank you. Epoxy to the armature. The contact was at the lever arm of R naught equals 9.4 centimeters. The height H shown in Figure 10, H equals 20.1 centimeters. Various values indicate the various values of the distance D between 0.05 and 2 centimeters were measured with the micrometer. The triangle of forces that shows that the horizontal component of the force applied to the plastic torque in the arm is mgd over h. So the dependence of d on the calibration torque is given by equation 16. The average suspension fiber of delta theta for two different d values required to null this out, or to null out this torque. The various twists up to 100 degrees was found to be given by equation 7. Mechanic theory yields the value of this measured of the balance and sensitivity to be twice of the observed. For this, or thus the tungsten fiber of a radius r equals 0.00635 centimeters and length of L equals 12.5 centimeters, possessing a tabulated modulus of torsional rigidity of E equals 14.81 times 10 to the 11 dynes per centimeter squared. As theory predicts, equation 18. For twist angles well in excess of 100 degrees, a nonlinearity response with the values tending tend toward agreement with equation 18 was observed, but we shall use the empirical calibration of equation 7 to describe more nearly linear range of the small angles. The physics of such nonlinearity, i.e. extra stiffness at small angles, was not investigated. It may have to do with the surface versus bulk properties of the tungsten in small diameter fibers. Comparison versus observation with theory. Our observed result in equation 15 can be compared with the two versions of Wesley's theory. In the simplest version, we use equation 3 treating the infinitesimal solenoid cross-section delta A as a finite area of 0.7126 centimeters squared of the 3/8 inch diameter cylinder magnet. Conversion of the torque.
Don't you love
ring-
how he uses two different systems of measurement in the same sentence? That his
Dude.
area is in metric, but the diameter there is in inch and imperial. Isn't that hilarious?
I'm just trying to figure out how many foot-pounds is 3/8 of an inch. Conversion of the ring torque to the armature torque can be crudely accomplished by multiplying the radius ratio B over R. Thus, equation 3 and the parameters already given, we have equation 19. Right? See, then we have a nice graph here. We have torque in degrees. Comparison of the theory, equation 10. Ordinate values of proportional to the torque. The torque magnet armature would have no absolute meaning. The abacus is the abscissa.
Abscissa.
Yeah, the abscissa, thank you, is the angle psi in the horizontal between the plane containing the toroid vertical members and the ring diameter at which the current is led in and out. Fitting the theory to the data is done by the least squares. The correlation is only 0.89 and the model selection criteria is a low 0.34. A closer theoretical approximation can be obtained by using the finite area integration of equation 13. We replace the area delta A delta A equals 0.7126 centimeters squared by the side, by the square of the side of the square of delta A. At the center radius, B equals 1.19 centimeters. The square can then be approximated by annular segment of the outer radius. D equals B plus the square of delta A over 2 equals 1.612 centimeters, and the inner radius equals radius C equals B minus the square of delta A over 2 equals 0.768 centimeters with an azimuth extent B delta psi equals B dot product of 2P equals 2 delta, or equals the square of delta A. Whence P equals the square root of delta A over 2B equals 0.3546 radian. Here.
You want a popcorn, Alan?
Sure. Pop.
I was about to spell him off when he got about 20. I was going to spell him off, but you can if you like.
Here, P, to remind the reader, is half the azimuthal sector subtended by the cylinder magnet at the armature's geometrical center. Thus, we have approximate values of the integration limits C, D, and P needed to evaluate the integral I in equation 13. The result of such evaluation, I equals 0.1798. Of course, a still more accurate value could be obtained by integrating over the exact circular shape of the magnet area A0, but this was deemed to require disproportionate effort considering the crudity of the measurements. The constant C has the value C equals 0.4 B0 I armature over pi equals 292.8 I amp. For our measured value, B0 equals 2300 Gauss. Consequently, from equation 13, the T-half magnets equal Ci, which is 52.6 I amps. The total torque on the magnets is twice this, yielding 105.3 dyne centimeter per amp. Compare it with the cruder theory in equation 19. This may be related to our observed result, equation 15, by using the balance calibration factor found in equation 17. Thus, the torque predicted by Wesley's theory should yield an angular twist of, as represented by delta theta over I amp predicted equals the T magnets over I amp times delta theta over T calibrated equals 105.3 times 0.08794 yields 9.26 degrees per amp. This compares reasonably well with the observed value of 10.5 degrees per amp. The simple theory value given in equation 19 yields a prediction of 8.465 degrees per amp, which is also in satisfactory agreement with observation, considering the roughness of both theory and experiment. So they got really close with both their equations approximations. They measured 10.5 and they calculated 9.6 and 8.5 basically. So far, empirical results may be said to confirm the Wesley theory. Unfortunately, honesty and an exaggerated respect for the whole truth compel me to mention that an observational attempt to confirm equation 10 failed. In brief, using the same magnet armature already described, suspended in the torsion balance, the encircling ring with attached current leads was rotated progressively through various values of the azimuthal angle. Is that phi? Is that like the cursive phi?
Psi.
Psi. The observed torque data are shown as gray circles in figure 11. The absolute values of the ordinates in this figure are not significant, only the relative values. They will be seen to follow roughly a cosine law as suggested by the numerator of equation 10. Unfortunately, the cosine enters also into the denominator of equation 10, with the consequence that the theoretical curve, shown by open stars in figure 11, departs strongly from the empirical data. Now, it is true that the theory, based on infinite length solenoids of infinitesimal cross section, poorly matches the observed case of 5-inch long cylinder magnets of 3/8 inch diameter. Yeah, that would probably give you some deviation. But an attempt to calculate numerically a more realistic theoretical approximation to the experimental parameters, though not successful, strongly suggested that no salvation is likely in this direction. The qualitative differences between the two curves in figure 11 are so great as to cast doubt on the theory. But I know of none better. At present, the matter must be left with the remark that the measurements are admittedly extremely crude and need to be repeated under conditions favoring better accuracy. I don't remember what equation 10 was, because he's basically saying that, equation 15 and 19 yielded correctly, but equation 10 didn't. But I don't remember what equation. What was equation? Before we read the summary, can we go look at equation 10 real quick?
Absolutely, sir. Yeah,
Yeah, it's right under Fig 5 with the roundy magnets. Keep going up.
Yep, there we go.
There it is. You go with the Newton. See, what they're doing with those magnets in figure 5 is they're trying to create as much proximity for as much of the stroke as possible, which is denoted by P on the upper left. That from when they turn the old phase on, from when the center of that pole north meets the input point where the current comes into the ring, that's where you begin to get torque for that 90 up to 90 degrees. And they want to put as much of that in direct proximity to that portion of the conduit in order to produce the most torque per phase.
Was this where he was saying infinite solenoids with infinite cross-sectional area serve as a poor representation of permanent magnets in whatever configuration they had?
Somewhat, but I think he's neglecting a fair bit of the geometry on the whole, and I think that's the source of some of his error in his guessing, etc.
Yeah, because the other equations yielded really close to what they measured, so it's kind of weird that there would be like one equation left out that was wrong. So probably did something wrong somewhere here, but the rest of it matched fairly well. But this was the one that he said the shape of the curves was too different to be correct. Okay. Well, can we go back to summary?
Skipping to summary. Beep, 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 beep. Summary located.
Marinov's invention definitely works as a motor. Independent observations not yet reported show that it works also as a generator. In other words, it generates a back EMF in rough agreement with the formula E back equals torque over amp times 2 pi frequency, where F is your.
Hang on one second. You're good. Continue.
Did you find your lighter, Ken?
where F is the frequency of shaft rotation in hertz. Wesley's theory of motor operation in terms of the vector potential A is roughly quantitatively confirmed by the present investigation. Our observed torque value being actually about 13% higher than theoretical. Now, this discrepancy is not considered as serious in view of the crudities of both theory and experiment. More serious is the qualitative disagreement shown in Figure 11. Other claims of Marinov, such as that no back EMF would be produced and that consequently the machine should work as a perpetuum mobile, have not been investigated and would appear to be invalid. With a dash of optimism, one can view Wesley's torque formula and the generalizations of it given here as providing an adequate theoretical basis for initial exploratory work with designs of various possible practical motor embodiments. The extreme simplicity of the design elements provides some inducement to pursue this. By concatenating half rings wired electrically in series, the torque can be augmented. This has been confirmed experimentally by Ligon. And continuous ring turning with use of brushes has been demonstrated by Quistra for the ring rotor, the magnet stator version of the motor. Also, the writer has demonstrated a multi-ring stator magnet rotor version that rotates continuously by simple commutation, current polarity reversal twice per cycle, and is self-starting in all but a very limited range of angular positions of the rotor. Quistra has made further observations that appear to refute the hypothesis that B-flux leakage is the driving mechanism of the motor, which that was from the intro where he was like, it's some people might want to say that,
That
even
flux
though
leak.
even though we know that all the Maxwell equations and Lorentz force law equations show that there should be no force acting on this ring, there's a force acting on the ring, but they might say that it's a flux leak. But, when we compare it to experiment, it doesn't make sense to say that. The Marinov motor seems possibly destined to give rise to a new generation of electrical machines, quite inexplicable in terms of flux leakage and other easy outs of the quote-unquote modern physicist. The idea that physicists move with the times is applicable only to their frontier flittings, not to their grasp of or concern for the foundations of their discipline. I should know better, but let me here challenge any physicist using the V cross B of the Lorentz force law to explain, no matter how the flux may be leaking and no matter where its vectors may point, how a vigorous driving force tangential to the current carrying ring is produced. Can you scroll down? For V, or the current vector I points always in the azimuthal direction around the ring. So there is no place along the ring at which substantial first order azimuthal force can be produced by a cross product involving B. V cross B can produce a transverse radial Hall effect voltage, but this is not a ponderomotive force and certainly not an azimuthal one. Also, del A over del T in the definition of the E field seems irrelevant to the observations. The total time derivative of the A vector is another matter, and that is the story Wesley has told. Doubtless there remains much more to be told, but first it must be learned. It is probably true that the development of electric motors as we know them owes more to empiricism than to theory. Often, only a small hint has been needed, as from the work of Faraday, to cause a fantastic blooming of practical consequences. If this does not happen with the Marinov motor, it will show that a fundamental retreat from intellectual initiative of our species, not to mention a loss of what used to be called Yankee ingenuity, has accompanied the fixation upon truth through theory, not to mention theories of everything, by which physicists of the late 20th century have sicklied o'er the native hue of resolution with the pale cast of thought. Acknowledgements. The writer wishes to thank
Yeah.
Phil Haig for witnessing and helping in data taking. He's indebted to Tim Ligon for copper gasket rings suitable for testing the motor concept, and to him and Jeff Kuistra for timely information about their independently observed results, ideas, and techniques. Graphic art assistance of R.J. Benish is gratefully acknowledged. The debt of all experimental investigators of this concept to J.P. Wesley is obvious, and of course Marinov himself is owed posthumous recognition. Let his name be associated forever with yet another practical demonstration of how spectacularly little is known of the wisest of us. The end.
Amen.
Hear ye.
Nice.
I like here what he said at the end and where he was like in the middle of it talking about the freaking Maxwell Einstein first order measurement mistake force, first order mistake force, and then this.
That was my
was
favorite part.
tasty.
Yeah, I mean, dude, he's right though. He's like, of electric motors, our development of like practical electric devices has definitely been made more through experimentation than through theory and writing on a blackboard. He's like, but now we're in a point where people don't care about that anymore. All they want to do is theorize stuff and say the math, right? And it's like we've clearly demonstrated that there's a force acting on this ring, and we've even made some math to describe it and gotten within 13% of what we measured using very crude measurements. It's obviously a motor. If this doesn't grow and more people don't start using this to develop stuff, it clearly demonstrates the retardation of our species when it comes to physics. Yeah, I mean,
Sterilization through purely academic approach.
yeah, I think it's very interesting. I don't really know what this vector A potential is though. Like I don't know what the A is. Like what's the A vector? I know what an E field is. I know what a B field is. I don't know what the A field or A vector that he turns into a field is. Like, what's the A?
Hold on
I
one
think he's
second.
calculating an area of interaction, rotor to stator, where the field is relevant to the other object.
Sanda.
If
If Cassandra's there, he might be able to help us out with where the old A vector is coming
Yeah,
from.
I think that's a great Bennett question.
That's his forte, some would say.
Cassandra. Yeah, Bennett, thanks for coming through for the reading night. Get his mute button on, but E is hold on. Let me see.
So this is this is the yeah. So
hey,
the
there it goes.
Hey, spaghetti.
Okay.
Welcome.
Well, I was consistent. I was on time at 9 o'clock. Had awful trouble trying to get the audio. I'm not sure what happened. I tried to connect through Discord, and this was being published on YouTube, right?
Yep.
And I couldn't get the audio to work until I went back to Discord, started all over, and then was able to make connection at about 9:30.
Oh, nice.
Dang.
Well, I mean, that was right after we started because we started late, so you didn't miss much. Cool.
I see that you dig down into the details, and I guess my summary of what the Marinov motor shows is that there is an ether vector potential. That's what the A vector is. Curl of A is equal to B by definition. And so you can have a, let's see, you could have an ether field that has a divergence, but not a curl. And if it doesn't have a curl, then it doesn't produce a magnetic field. But you could still have an ether field present if it was the source, as if it were if it had a divergence which wasn't zero.
Yeah.
So one of the questions was, what is the A vector? It is the ether vector that is the basis, the foundation of electromagnetism, because if you take the curl of A, you get B. If you take the curl of B, you get E. So there is a pyramid of hierarchy in electromagnetism, which starts with the A vector, then goes up to the magnetic field vector B, and then up to E. And that's a progression that is based on the assumption that the lowest possible electromagnetic field is A, the vector potential, because from that you can basically generate all of the laws of Maxwell.
Wow.
And if you use A, then it's called the Maxwell-Hertz equations. And
Mm.
there's another paper which Alan has posted, and I think you discussed, where Phipps shows that the Maxwell-Hertz laws are Galilean invariant. There is no Lorentz transformation that is necessary in order to predict all the laws of electromagnetism if you use the A vector potential. That is, if you use the Maxwell-Hertz form. Of course, what does modern physics do? It ignores the A vector potential and says that it's just a curiosity, or some people say it doesn't exist. So all they work with is E and B and ignore the A.
Wow. Thank you so much for that explanation. That's yeah, I got it pulled up right here from ChatGPT, and then I remembered I read it earlier in the paper because B equals nabla A, and nabla cross A is the curl of A. And having just reviewed calculus 3 not that long ago, like that's so interesting that you can literally derive the B field from this A vector potential. It's like, what vector of what though? Potential of what, right? Because when we think potential, we think like electric potential, right? But then you've got the vector potential A, like how wonder how that's defined. It it's describing the magnetic field in terms of potential. So when this potential has when this field describing this potential has curl, it results in magnetism. So there's like a right hand rule that we can apply to the ether to yield magnetism. And then, there's a right hand rule relating magnetism and electricity as well. Huh.
Well, it's not just rotation. If there's a change in the rotation of the A field, it produces a magnetic field. So this underlying ether has to change its rotation, which would cause it then a curl to be non-zero. And that is the magnetic field. And the magnetic field, in turn, has the same property. The curl of B is equal to E.
Oh my gosh. The acceleration of the ether yields magnetism.
Mm,
Uh, yes, a change, yes.
Oh,
wow.
whoa.
Actually, it's quite beautiful, isn't it?
Yes.
A
Yeah.
curl of A produces B, the curl of B produces E. And so you have a progression, an upward progression from the most fundamental field, which is not E and B, which most mainstream physicists think is the basis for the electromagnetic properties. But the real fundamental field is the A field, A vector potential. And it's the A vector potential that exists between the toroid at the center of the Marinov motor and the ring that's being tested for the torque. right? You want to produce a rotation of that ring using the Lorentz force law. But if there's no magnetic field outside the toroid, there should be no Lorentz force. And as you went through in the paper, Phipps proves that there is a Lorentz force, even though there is no measured magnetic field. The explanation is that there is an A vector potential.
But what does that physically connect to in physical reality? What's the A describing? He doesn't even bring that up in the paper. He just says that here's A. A
Well,
does it.
he hasn't made that connection.
Why? Wait a second. But they're applying a current. They're hooking wires up and applying a DC current into the toroid so that there's a magnetic field moving around it. Wait a second.
Not around it, inside.
Inside of it. Yeah. Around the inside of it. That's what I mean. And when that happens, wait, the motion of those charges produces a magnetic field that is moving, and it's accelerating the ether inside of it. And the ether inside of it's moving, and it's continuous around it as well, which is why the A field changes outside of it.
Ether is everywhere.
Right. Oh my gosh. The moving charges induce a changing magnetic field inside the toroid, which accelerates the ether and causes the A field to change, which gives it curl, which produces a magnetic field outside. But they don't detect a magnetic field outside. It's literally being manifested as a direct force of ether in motion.
Right.
The ether is pushing the ring.
Yes.
What
ultimately, you see, when you say, well, it's an electric force, right, with charges. As I pointed out, the electric field can be reduced to the change to the curl of the magnetic field, and the magnetic field, the curl of A. So once again, even when you have electrostatics, you have the influence of the A field influencing the electric field. Difference is that the rotations are the rotations of the atomic particles, not the mass motion of electrons in a wire. You see the difference? You have electric currents all the time in the circulation of electrons around the nucleus of the atoms.
Mm-hmm.
So you have a rotation even when you have objects that appear to be stationary at the atomic level. They're all rotating. They all have spin. So they all have magnetic fields, and that can be traced to the curl of the A field.
I think what's not being addressed here are the orders of magnitude of force one to the next.
That is true. What the Marinov motor proves is that although there is the Maxwell laws would not predict a Lorentz force on the ring around the toroid, that there is an electromagnetic force due to the A vector potential, and the change in the A vector potential, the change in rotation will cause a Lorentz force.
Doesn't Dr. Bennett? Wouldn't this show that they're actually able to create a small because of the applying the current? when they apply the current and the charges are moving and it's affecting the magnetic field inside of the toroid, that means that that magnetic field by the applied current is actually evoking a change in the ether, in the motion of the ether. And then when that ether motion is changed, it's then re-inducing a change in the magnetic force, but not via a detectable magnetic field, because there shouldn't be one. I don't know if they actually like took out some kind of like magnetic field detector instrument or something, but there shouldn't be a magnetic field out there, but we have a Lorentz force without a field. Like it's a Lorentz force without a field, so to speak.
Yeah, let me ask you this. I wasn't present for the full discussion. I only joined when you were on the last page, basically. Did he consider what would happen if the toroid rotated?
Ye, ye, well, there's
He
two
implied
setups.
that there would be a different torque value produced, and that was one of the things about which I disagreed.
Well, in terms of what we've just discussed, if you rotate the toroid, you rotate the A field around the toroid, and that will generate a magnetic field. So you will detect a magnetic field if you rotate the toroid. But if the toroid is stationary, and by stationary I mean what? Stationary in the Earth's reference frame.
Right, the
All right.
lab.
That goes back to Newton's bucket and all of the experiments that prove that the laws of physics are only valid in the Earth frame. Yeah. So if you rotate the toroid, you're moving the A. It will produce then a change in rotation, and if you have a change in the rotation of A, and the curl is non-zero, and the curl of A is B. So you will detect a magnetic field if you rotate the toroid.
But inside the toroid, right? Not outside of it.
No, outside the toroid.
Well, are you saying with the current applied, right? While the current's being
Yeah,
applied.
yes, with the magnetic field inside the toroid. Yes.
Okay, yeah. See, there's two setups he did. So the first, he had the toroid fixed in place, and when he applied the current, the ring was able to spin. And then the second one, he put the toroid, he made the toroid hang from what's basically a torsion balance and held the ring in place, and it caused the toroid magnet to twist and put torsion on the wire, up to 90 degrees, right? So,
That's interesting.
mhm. Well, 90
Oh,
degrees would where it would become perpendicular and it would experience a zero net force, but via the cross product of the would it be the normal vector or the trying to think about the geometry.
This is where I address the variability of flux within the conductor itself surrounding the toroid. You know, that the conductor itself has inherent undeniable resistance, and that flux entering is not the same as flux exiting, also creating planar asymmetry on that basis.
well, it'd
But
be interesting if he had done that, if he had spun the toroid.
well, if we did spin the toroid and we don't think about the A vector of the A field, right? We just think about the standard E field and B field. If we have moving charges going around the permanent toroid magnet and we spin the permanent toroid magnet, the regular Maxwell equations would also predict a magnetic field would be produced, wouldn't they?
Yeah, if you have the charges inside the toroid rotating, it would produce a magnetic field.
So they would. So I feel like if you were to rotate the toroid magnet while the charges are going, I think that that would produce the same prediction as using the A field, right? Isn't it?
Mm-hmm.
So basically, the only way that he's able to elucidate a difference is by keeping the toroid magnet stationary. Okay, so that's like the Newton's bucket difference right there. Like when we keep it stationary and we add charge, which is like the water or whatever. I guess actually the ether would be the water in this case. The A field would be the water, but I digress. Uh,
This is
huh.
this Marinov motor is consistent with the Aharonov-Bohm effect, which I covered in one of the talks. The they set up a magnetic field in a region in a solenoid, and it is an electromagnet, and the magnetic field should be zero outside the solenoid. But if they use electron beams through the area around the solenoid, the electron beams are,
Or what?
there is a magnetic field present that can't be detected. And in order to prove that there is a magnetic field present, you have to use quantum mechanics.
Well,
So the experiment is a blend of classical mechanics and quantum mechanics.
wait,
But in that
It ba-
geometric analysis, though, I think there could be a lack of regard for the thing, the construct that is the coil, physically speaking, that you have to have an insulated conductor in order to achieve that geometry to begin with. And what they're measuring on the outside of the coil necessarily could be what they're calling flux leakage, in another context here, of course, where it could merely be the gaps in between the wires necessarily caused by the insulation that's on them to allow measurement of the field inside it from outside of it.
yeah, I think in the experiment they put a metal around the solenoid in order to suppress any magnetic field leakage from.
In the form of hysteresis on the body itself.
Well, I don't know if it's a diamagnetic material. Have to go back to look at the experiment itself.
I think for
But
the
I
most
think,
dampering, I would encourage ferric material.
okay, whatever it was, they seemed confident that there was no magnetic field outside the solenoid
Uh,
when they tested the electron beams.
You cut out for a moment when you were explaining it. Did you say that the electron beams deflected? Because right when you said electron beams, they're like for about 3 or 4 seconds you got cut out.
Okay, I'm sorry about that. The electron beams were not deflected when there was no magnetic field in the solenoid. When they turned on the solenoid, producing a magnetic field inside, and as I'm saying, there is a concern that there is a leakage because the magnetic field has to be complete, has to be circular. So, however they suppressed it, I'm not sure. But when you read the experiment, you get the idea that they're confident that there was no magnetic field outside the solenoid when they used when they tested the electron beams. And in order to predict the deflection, they had to use Schrodinger's equation, which is quantum mechanics. And that was a key experiment in connecting classical electromagnetism with the modern quantum mechanics.
Well, so they basically put this applied a current into the solenoid, got a magnetic field going inside of it, put it inside of a Faraday cage, and then when they shot
Okay.
they shot the electron beams at the encaged solenoid before the electron beam was able to reach the perimeter. It was deflected. Is what you're saying?
Yeah, but the Faraday cage would only suppress waves,
Right, because okay.
not a steady
Uh,
field. The
So
Faraday
Pizzo, I don't
field would
think
not.
it's Pizzo. I don't think it's a matter of aiming the beams at the coil. More like the beam is probably aligned parallel to the axis of the B field and fired over top of the exterior of the coil, perpendicular to the lines. That would be
Okay.
my guess.
Yeah, I wasn't thinking about the geometry much. I was just thinking like they shoot it towards it, it gets near it, it moves away, it deflects away when it encounters, a magnetic field that shouldn't be there, basically. Huh. And I mean, invoking, Schrodinger's wave mechanics in order to predict this, Dr. Bennett. I mean, Schrodinger himself, I don't know if you're familiar with It's BS. He has a Twitter channel and a YouTube page that produces some pretty good content around this uh, origin of quantum mechanics. But, Schrodinger himself made fun of quantum mechanics because he thought it was silly because they actually took his wave mechanics, they took his Hamiltonian operator, the Hamiltonian integral that he derived. They put absolute value signs around it and then squared it and turned that into a probability density function. And that's what they used for their quantum mechanics to say this is the position of an electron particle. But Schrodinger was actually trying to describe matter in terms of waves. And it was the wave function that itself, not the quantum mechanical one that Max Born or whoever turned it into, but the original one that was able to successfully predict things like, I think it was the line spectra of light emissions coming from the nucleus of atoms that he was awarded for. So the equation in its original formulation was actually what was able to successfully predict, the behavior of matter and interactions of matter with, electromagnetic effects. I I know that's like a separate conversation, but I just wanted to say it because I think they've basically like co-opted Schrodinger's work, but Schrodinger did not approve of their interpretation of his work because he when he originally formulated it, he believed his wave mechanical equations were the real depiction. Like he believed that the wave part was the real part. The quantization into points was the theoretical part, and that's why he made his Schrodinger's cat analogy. It wasn't trying to describe quantum mechanics in such a way saying it was nice. He was actually making fun, like laughing at quantum mechanics when he made the Schrodinger's cat analogy.
And
Yeah,
their embrace of it was a reason for leasing.
he was challenging the Bohr theory of quantum mechanics, so-called classical or conventional quantum mechanics. How could the
Yeah.
cat be both dead and alive at the same time?
And it doesn't die until you actually open the box.
Yeah, or it stays alive, either one.
Yeah, right.
But you don't know until you do the experiment, until you actually open the box.
That's such an esoteric mysticism type interpretation. Like it just doesn't. That's so. I can't believe that is accepted as like reality by physicists.
It's sleight of hand, and mainstream eats it up.
They do love their sleight of hand.
So what's your take, Dr. Bennett? I mean, the whole duality principle, which is like, an esoteric principle in its origins anyway, and it's applied through all of this stuff that they do outside of the realm of science. I mean, in artificially injecting this duality principle into physics, like what's your take on that? This Copenhagen probabilistic interpretation of reality.
Yeah, well, I touched on this when I indicated that the highest level of knowledge domain is theology, because in theology you have uh, knowledge that is given to you, not that has to be discovered. The next level down from theology is philosophy, and I promoted the philosophy of realism, which was basically taught by Aristotle and developed in the Middle Ages into a philosophy called scholasticism, and I covered that in the talks.
Mm-hmm.
The theory of Aristotle was that you have matter and prime matter and form, and prime matter is matter that has no particular properties, but has the potential to to be to be anything. An example of potential becoming actual reality would be water has the potential to become ice or steam. It doesn't have any potential to be water because it already is water. All right. And if certain physical properties are present, the correct pressure, volume, and temperature, you can convert water into ice. So you have the potential of water to become ice. The potential is the property of matter, that is something that exists and having the ability to change. The idea is called hylomorphism. Hylo means matter, and morphism means shape in Greek. So what you have in ether is what I'm promoting is ether is the potential for something that exists but has no particular attributes, and it has the potential to become anything. So it has existence, because if it didn't exist, it wouldn't have any potential. But it doesn't have any definite measurable qualities. Water has definite properties. It has the properties of a fluid, and it has the potential to become gas or the potential to become a solid, ice. But if we ask what was the cause of water, we can say that it came from ether, where ether had the potential to be anything, and the right conditions were present for the ether to become water. That is, to become molecules.
To become matter.
Yeah, this is the theory of change. When philosophers in Greece asked, what happens when something changes? The model that Aristotle used was this one I'm describing, hylomorphism, where an object has a potential to become something else when certain conditions, called triggers, or more simply, causes. So when the cause of a action is present, its potential is activated. And in the case that I'm using, water becoming ice, when you have the right conditions, water can become ice. But that's something that already exists as a particular form of ether, becoming another form of ether. If we talk about prime matter, prime means first, then I'm identifying that as ether, which has the potential to become anything.
So what do going up the tree from physics to philosophy, but you're at philosophy right now. Theology is above that. So what do you think that the voice of God reverberated through the ether and transformed it into matter, which was the act of creation?
Well, exactly how creation occurred, which is a one-time event. We could model that by saying that there was God had the potentials to create anything, and he selected exactly what would be the potentials for the reality that he wanted to create. Okay, so he could have made people with 3 heads, but he chose not to. Okay, so there was a choice of what existence would be, what the properties of the created objects would be. So that fits in with the theology. If you examine Genesis, it talks about creating form. If you look at the Hebrew verbs, some of them indicate that a form was created, a template, in other words, for the creation of other things.
Yeah, the
Other
earth
things
was.
were created. Other
Sorry.
things were created directly. So if you look at the 2 different types of Hebrew verbs, you can distinguish those that are used to create new reality. For example, Adam and Eve had the potential to create new humans, right? So that is a potential that they were given to create new forms. If they didn't have that, they would have been the first and the last humans.
Yeah, are you making pointing kind of to in the beginning God created the heaven and the earth was without form and void?
Hmm.
I see. Okay. Yeah, it's actually all quite interesting. I really appreciate you like breaking down the A field and its relation to this, but then kind of tying it back to. I appreciate the answer to the question about your philosophical paradigm, and I also ascribe to realism, physical determinism, so to speak, and some people call it that. It is what it is, and it's not what it's not. It's not a superposition of everything it could be at all times, like Copenhagen says. Um,
It's the belief that there's a real world that exists independent of what we observe. In other words, we don't create a world in our
by
mind,
observing.
which is idealism. We
You're
don't
like,
create
sorry, go ahead. I'm just laughing.
we don't create a world in our mind that doesn't exist or have its foundation in reality. All of the things that we learn come through with the senses. And
Uh,
if you were deprived of all your sensory experience, you wouldn't have any model of the world because you would have no way of knowing the existence of an external world.
but the world would still be there whether you sensed it or not.
That's right. Yeah, it exists. Yes.
It's like the physicists believe in simulation theory or something. It's so weird.
Yeah. I think that there's a lot of things you can solve with philosophy. Like I think I talked about infinity in one of the talks, about how physicists and mathematicians, well, let's say physicists, talk about the existence of the world, whether the world is infinite. Philosophers, the answer is very simple. Infinity is not a number. It is the concept of something which is unchangeable, which is something that almost none of the current scientists realize, or at least accept
Knowledge.
publicly, I would say. Okay.
Mm-hmm.
The physicists think that the world simply means more and more of what exists without limit. But to the philosopher, at least the realist philosopher, a number system, for example, is infinite because if you try to add another number to it, it doesn't change. Because any number you can think of already exists in the set of, let's say, integers, the set of integers.
Oh yeah, when they're talking about different sets of infinity, that's a completely theoretical concept. You can never get there because where would you put it?
Yeah, you can't add anything to an infinite set. So the key idea is not that it's totally big, that it's big beyond limit. Key philosophical idea is that something that's infinite is unchangeable, immutable.
Uh,
The world we observe, is it mutable or immutable?
Definitely mutable.
Exactly. So it's finite.
Right. Yeah, I mean,
I agree
common
with
So-
that interpretation of the word infinity only so far as that it is beyond our ability to perceive incremental change.
Okay, that's one definition.
You know, yeah.
As I
Well,
said, the realist would say that anything that's infinite can't be changed because you can't add anything to it that it doesn't already have. If it's unchangeable, that doesn't reflect what we see in the world around us. We see a changeable world.
yeah, it's almost like if you use the thought of it being all encompassing, like if you just simplify the entire existence of everything down to like a little sphere. Well, adding to infinity would be like taking something from inside the sphere and trying to add it to the inside of the sphere, but it's already in there. You can't change the sphere from what's already in it. You'd have to take something
Uh-huh.
from outside.
Yeah, but what's
Well,
outside?
Yeah, it's
how
not.
about we
It's,
get this a little
right,
back
exactly.
onto the rails here? Alan's got a video that I sent out ready to watch. It's about 2.5 minutes long to finish up the practical side of the Marinov motor. And Toby specifically asked me to put together a review of sorts of the Phipps paper and specific to in regard to Marinov. So I'd like to get to that if we could.
Yeah, for
Absolutely.
sure. I appreciate the Cassandar, Dr. Bennett. Thank you for the talk. 10 seconds left. I'll get this on, and then we'll get off on the way. You are. I take it you're a believer in Jesus Christ, Dr. Bennett.
Yes, I am.
All right. I appreciate that answer. Thank you for your time.
All right, cool. So we're gonna head up your boy Plenum88. He did a Marinov motor experiment a couple of years ago. I'll say his channel's pretty old. So here we go. Enjoy.
Okay, we're going to try and show continuous rotation here by pulsing the DC. Yeah, this is the
Notice
Marinov
that he's
motor.
only
It's running
applying
about
power here to
250
one of the 4
270
quadrants.
RPM right now. Just got the pulsing circuit. You can see the pulses.
Whose video is
Driving it
this?
right now. It's about 30.
This is from a YouTube channel called Plenum88.
Plenum?
6% duty cycle.
Yep,
And
very worth checking out.
we've got-
PLENUM.
5
He does
volts
a
at
bunch
4
of videos like
amps
this.
times 0.36 is about 7 and change in the watts driving it. And we've got a flashlight to a photocell, which is, and a rotating flag, which is setting up the duty cycle.
So he.
Adjust the brushes again. Now it's running much better. So a lot of the problem is brush resistance. What are we doing now? We're doing about maybe 150 milliseconds, something like that.
Alrighty. So keeping in mind that I'm only looking at about 2 hours of preparatory work to put this little 2-pager together. I just wanted to rack count.
Stone.
Can you hear me?
Yeah. Did you want me to pull up the paper to go up through like specific points? Or do you just
Yeah,
wanna...
you could, by all means, you could. I do it page by page. So sure, that would be
Perfect.
great. Starting
Yeah.
with page 1.
Absolutely.
Yeah, right up at the top, which is why I recommended the piezo start by reading the abstract, because when I read an abstract that makes use of an expression like roughly agrees, personally, I get the impression that there is inadequate precision in the analysis I'm reading with respect to quantification. And I want to preface all of this with this is, as Steve Martin would say, this is what I believe. And my tune very well may change with additional experience in the lab, which I plan to run down the road with in the coming days. So this is all preparatory review in that regard. But right after that abstract there, this is where the road diverges between that of the path walked by the academician and that of the practical engineer. He introduces the context where he says that a permanent magnet of roughly toroidal shape entirely enclosing its B B-field flux is placed inside a conducting ring. And we've just actually had a conversation about that, about measuring flux inside of it, outside of it, what they toss away into the realm of flux leakage and that kind of thing. I view a lot of that as hypothetical and not actually demonstrated, especially in this arena. So hopefully I will have some more to report on that later. But it has not been my experience thus far in the practical world that this is the case. After tonight, that could be another story. Because if it were the case, then there would be no interaction whatsoever between the toroid's magnetic lines of force in the field created by the conducting ring itself. But I do like how early on in his paper, he makes the distinction between the two parts in terms of their function as rotor and stator. So when we were watching that video we just watched, I think that guy made an incorrect choice to try and spin the rotor using brushed commutation. And I'm going to give you another reason for why I think that's the wrong choice shortly. One other departure from the fundamental design I noticed in this video that we just watched has to do with the magnetic toroid, quote, itself. His magnet stator, the one you just see there, is actually made up of many pieces, many magnets. And the block line in question, in terms of the plane, diagrammatically speaking, is offset vertically. It's actually a little bit below the ring's planar line of motion in terms of the electrical flux, that they are not lined up. So there's a bit of asymmetricality there that we need to regard in the practical sense of what we were just watching. And that is just the beginning of a list of ways in which I think his use of those magnets is a significant departure from the actual Marinov design. But by the end of the video, in case you weren't writing them down, he was using a duty cycle of roughly 27% and managing about 400 RPM out of his spin rate. And he's driving it with 14 volts, where a 100% duty cycle would involve 3 amps of current flowing through at all times. And that would give you a power consumption of 52 watts. And in comparison, at the outset of my own development of the Bedini and others pulse DC types of technology and the like, I was using roughly a fifth of that wattage at 3/4 of that voltage to achieve spin rates in excess of 3,000 RPM, where the rotor mass was roughly 20 to 30 times what you see him spinning there in terms of his conduit. So halfway through page 1 here, he mentions that the current value of I flows through 1/2 of the ring. Now, to me, when I'm looking at that diagram, that just in terms of ordination, pure ordination and analysis, that seems mathematically incorrect. If it's half the ring, it should be half the current, meaning that 2I should never show coming away from the battery. Coming away from the battery with a single conduit, that should have just been I. And going through half of the ring, that should have been 1/2 I, going around each side of the ring. To me, that just makes more arithmetic sense. And so regarding the passage of current through the ring, to say that everything is electrically neutral seems a little counterintuitive in the purely geometric sense. And I don't know, you make your own decisions on that, but citing that in an ideal toroid, magnetic flux is entirely confined within the toroid so that none is present at the position where the current going through the ring. Therefore, asserting that the B field vector potential would be 0, to me, that seems quite incorrect. I state this out of regard for how even in a typical motor design, the torque produced by the motor is function of the proximity of these two elements. So in turn, we can see even in the basic diagram, and he does cite it further on in this paper, that proximity is clearly a first order factor. And he cites a practical requisite of flux leakage as a second order, weak and random phenomenon. However, I think it is more a matter of proximity of the flux within the toroid to the flux in the conduit, which is the ring surrounding it. So as we go to page 2, after showing the same simplified diagram, he states that the B flux is largely contained within the toroid, with no attempt to quantify this containment or lack thereof. While mentioning Maxwell, he cites the need to look within the toroid examination of the flux lines in order to determine handedness, left hand, right hand, which is a requisite in the analysis. But then he begins to walk the mainstream path when he evokes what he calls tiny current whirls and assumes the existence, or presumes, I guess, the existence of electron spins in his explanation of the electromagnetic effect we're seeing. And I don't think he's doing us any favors here in his attempt to keep things clear. In terms of figure 1 and ring placement, I think he ignores the phenomenon of the block line in address of what he calls magnetization current and gives it the same attributes as real current. I take that to mean that he's referring to electrical current. So technically, at the block line, I see this as a place in the loop where what he is calling magnetization current would essentially be 0. And in practical prototyping of this motor, I think it might be wise to change the heights between the halves of the ring itself, which pass around the magnetic toroid, and move them in opposite directions away from the block line, one up, one down, in order to produce an entirely different, possibly far more efficient method of torque production. So again, this is something that I hope to test here in the lab soon. Personally, I think it's inappropriate to make comparisons between this geometry and that of a solenoid. Hopefully, I will be able to provide physical support of that assertion again soon. Finally, at the end of page 2, he makes reference to action at a distance. But as you can see in figure 1, there's no reference to anything but polarity and current. No reference to distance or proportion thereof. So on to page 3. Again, at the beginning, he immediately uses the words presumably and would many times in the description of real currents and their effect on the ring. And there he goes again with the term essentially equivalent and general inference. These are the phrases of the academician. He makes use of many more similar terms on page 3 before he even gets to the use of mathematical formulae. So I won't be addressing those parts of the paper. 4, I do commend his choice to take the C factor out of the formulae from this point onward to some extent. This is something I also mentioned in reviewing the Wesley paper, but things have gone on a bit long here. I don't think we're going to get to that. But I'm not so sure that he needed to invoke the use of several other formulae in order to justify it. But that's just me, I'm sure. His use of the expression velocity with respect to the observer's inertial system strikes me again as inappropriate to the analysis of this system, since everything here should be taking place with respect to the inertial system of the stator of the motor and not any detection instrument which might be used. I do, however, give him extra points for his confession that any perceived need for application of total time derivatives bears no application to the practical, and that first order approximations take preemptive precedence. Major points. Page 5, again, in his torque formulas section, he makes use of the value 2i, and I just went over that and why that's an unnecessary coefficient. And it overly complicates things from there on out in his formulae in terms of how to perceive it mentally and just judge what he's trying to say. And as we move on to page 6, we see that he agrees. Something didn't go down with the way this went to page, but it's that he's using an apples to apples comparison with the solenoid, and that assertion, not certain. Okay, so he agrees with my assertion that apples to apples comparison with the solenoid simply does not really fit the bill here. On to page 6, given what I've already pointed out regarding the construction of his formulae, I don't think it's necessary to address the rest of his mathematics. But by the end of page 6, he begins to use his imagination, direct quote, and I don't know, guys, that's where you lose me. But on to page 7, in echo of my comments about the block line on page 2, we do see on page 7 where he begins to address an azimuthal angle in description of the generated torque force due to the current flow around the magnet toroid. But out of regard for what I pointed on page 2, I don't think he's quite hitting the nail on the head here. And I imagine I'll be going into a fair bit more detail after I have a big dance with the practical in the lab. I do like his suggestion regarding wiring half rings in series in order to double the torque. And that is something I intend to investigate, probably with some more articulate design in the 3D printing department here at home. And also integrate what I just mentioned about offsetting the two conduits vertically with respect to the diagram and where the block line actually sits. I think we can get a lot more torque out of it by doing such a thing. And I'm guessing by what he says at the end of that paragraph that my intervention is precisely the thing he was anticipating. So I'm going to meet him at his level of need there. On to page 8, I do agree with his assertion that modification of the cross-sectional shape of the toroid can be manipulated in order to improve net torque per stroke, since rotor and stator proximity are the key to optimal torque production. And it generally follows that the closer one can be placed to the other for longer spans of the stroke, the more torque is generally produced. And that's what we see in his diagrams farther down, where he's got magnets that are close to the wire for more of the travel. but I don't necessarily agree with his visual representation of what he calls Amperian current loops, which are labeled in figure 4b. On page 9, at the end of it by the final paragraph, he cites a difference in the torque sum depending on which of the two parts of the motor is the stator. And I believe Dr. Bennett just asked about that as well. Personally, instinctively, I disagree entirely with this as a fundamental premise. Perhaps with a much larger budget, and where I'm going to get that money from in order to do such a thing is anyone's guess, I might be able to expand more on the potentials in this technology in a practical mode. And speaking of the practical, I would, as a final note, take you back to page 5, where he begins to speak on torque formulae. Notice that with equation 3, he begins in its description with citation of units of measurement where the magnetic strength is in Gauss and the current is in amps. However, he then converts his current and suggests that the torque be measured in terms of dyne centimeters, whereas he does at least mention the conversion in terms of the exponent, negative. He makes no comment as to the implications in regard to practical design. In removal of the exponent and expressing that relation in terms of a pure integer, we find that 1 foot-pound of torque comes to roughly 13.5 million dyne centimeters. To me, this loudly suggests that any attempts to develop this technology and implement it in a real-world motor design will simply turn out to be a complete waste of time, where we are supplying it with amps of current, in his case, 200 amps of current with 2,300 Gauss in the magnetic side to produce this near infinitesimally small amounts of torque. Naturally, in my attempts to replicate this technology, even in a simple moto prototype, I hope to find out that this assumption is completely incorrect. But time will tell. Indeed, time will tell, as long as I'm able to get to it and able. But those are my upfront preliminary review points of the Phipps paper. Hope that all made sense to you guys, and I'm open to questions on that too, of course.
Well, thanks,
Many
Stone.
many potential sources of error seems to be that the experiment would need to be done in a very, very precise, controlled fashion to elucidate very precisely the specific
No,
effects.
I disagree, Pizzo. No, I don't think that's true at all. And the 2.5-minute video is evidence to the contrary, that this guy used a collection of magnets to produce his ring. His flux conduit was offset with respect to the block line. He didn't have 4 poles, just north-south and north-south on this thing. He had more like 12. And he's still producing the effect. So no, I don't think there is such a grand need for extreme precision in order to produce truth. Not at all.
No, I'm saying in terms of, you were talking about the proximity of the flux of the inner toroid versus the flux of the outer ring, and coming in proximity to each other, and like as if when those fields collide with each other, it would produce interaction effects, which would produce a torque. Was I gathering that correctly?
Well, that's the same for any motor design with these types of mechanics involved. That gap is everything.
Okay. So that's what
And
I was
if you go
talking about.
back and take a look at that 2.5-minute thing again on your own, you will especially note it in his first attempt when he shows it spinning really slow and he's just kind of dicking with it. The gap changes from 2 millimeters to nearly 8 per cycle, and back and forth, and back and forth. That his gap is all over the place, and he's still producing some kind of torque. But yeah, gap is everything in terms of the efficiency of that production.
So that's what I was saying in terms of precision, is being able to control for that gap in such a way that you could elucidate whether the cause of this effect was a rubbing of the field, so to speak, or of a vector A potential, as is suggested by Phipps.
Well, again, I think that takes us back to my observation when we were talking to Dr. Bennett a minute ago, that I don't think any regard here has been given to orders of magnitude of the forces you translate between here.
Wasn't that what Phipps was predicting within 13%? And then he said the 13% is not that big of a deal because we're making very rough measurements here in our setup or something along those lines.
I'm not really sure where he got the 13% from. I mean, that's again, how precise is his measurement and how precise, like, frankly, Pizzo, I think a lot of this analysis is lacking, that we only saw the output of the current going through the conduit in terms of a square wave. And he didn't ever zoom in to show us precisely what's happening at the microvolt level during the off phase relative to how fast it was spinning, even in successive examples. I think there's also a fair bit, like Marinov's focus on this was that, oh, there's no back EMF. Oh, yeah, sure. But frankly, in any motor style like this, one element that I personally think is tremendously, tragically underdeveloped is what to do with the flux blowing through the conduits when you're watching it spin during the off phase, that there's no other secondary switching going on to harness that. That if there is no back EMF there, then what you could necessarily pull out, even at the microvolt level, would technically be, quote, for free. And exploitation on that level, again, this is another arena where I think it is just tragically underdeveloped.
Always back to that back EMF, aren't we, Stone?
Very much. Yeah, we are. Again, any other questions, people? It's a pretty large door.
Yeah, interesting. I'm. I mean, I just find it hard to reconcile. Like, I don't really have a huge dog in the fight because I just read this paper yesterday, of course, but I do find it kind of difficult to reconcile, like, looking at his, saying if we, instead of evaluating this off of Maxwell, if we evaluate this off of Hertz and the A field and start there and math it out, he predicted like 9 point, it was like, wasn't it like 9.6 amps or something, and they ended up measuring like 10.5.
Per degree of motion in the
Yeah,
rotor.
that was like the 13%
Mhm.
deviation or whatever.
Yeah, but is that even enough to overcome brush commutator friction? You know what I mean? Using that many amps? But what are the prospects is my question. And hopefully, by the end of my prototyping phase, I will be able to show you some.
What's your idea when you are going to test
That
this
sounds awesome.
stone to control for the A field being the cause or not?
Probably none at all in that area. Because the only thing that he's controlling with his switching is the E field, right? That's the control.
Shouldn't you be able, in theory, to measure the effect of the magnetic field coming from the toroid ring magnet and see where it extends in space in order to know
But
whether
that's a
it,
static thing, right?
well, when you have the current flowing, it's not.
Well, no, it absolutely is. And so is the orientation of the flux conduits themselves. Oh, I stumped him.
Well, I'm just wondering if there's any situation in like if you're doing this experiment to like try to elucidate the cause of this force driving the rotor, then wouldn't you have to be able to set it up in such a way that it could be this or it could be that and test for both?
Well, I do agree in principle that the object, the name of the game here, is to isolate as many factors as you can and make decisions or conclusions empirically based that tell you which of them are involved in torque production and which are not. I'll grant you that. But then there's the practicality of it. Like there's a point, I don't know if it's in the Wesley paper or somewhere else I read, to do with the Marinov, that they said, okay, well, we don't have to worry about brush commutation. All we have to do is have trenches of mercury for the conduit. So then we can just drop a wire into it. But that's just so impractical when it comes to actual real world motor design. Like it's not a gee here thanks kind of thing. You're not helping anybody by suggesting that in any practical way. And some of what you're just saying strikes me in the same way.
Okay. I don't have the capability to test this, man. I mean, there's nothing I have access to right now to be able to test it. So I would love
Yeah.
for you to do it.
Awesome. And I think I may even have, I know I have at least one. Hopefully I have the pair. I have some neodymium ferric boron rods that are about 2.5 to 3 inches long and about 3/8 in diameter. And I think I also bought a pair of, I don't know if they're iron or they're samarium cobalt, but they are the dark unpolished animal. And to connect them, I also happen to have a fair bit of transformer lamination steel, which I can fabricate and fit to those, and probably make 2 versions of those connectors. One that are, staggered or soldered rather, welded together, and one set that are laminated completely separate, where only the top layer comes in contact physically with the magnets, and see if that makes a difference as well. Is it purely the magnetic influence, or is there something else as well, physical, going through the loop?
Yeah. Once
Personally, I
again,
think we're going to make more progress by offsetting the vertical heights of the conduits with respect to the block line across the
well,
middle.
well, the point you were making about like what are the magnitudes we're dealing with and how do we know like based on what the magnitudes might be if we can reduce the cause of the force to that or not. I was kind of thinking of that point in terms of uh, if the cause is the magnetic flux leaking and then interacting with the field of the ring, or if it's the vector potential field, right? In both cases, like let's say it's a very small magnitude in like the vector potential field case, we would need to be pretty precise with our measurements in order to know. That's why I was talking about the precision, like how we can produce the force with very little precision. That's accepted, but in order to elucidate like the exclusive cause of the force in terms of like the mingling of the fields or the vector potential being the cause, I think that's where the precision becomes more necessary.
Well, I agree. And where in the paper I read that he changed his unit of measurement from foot-pounds of torque to dyne centimeters, for me, that's when the bottom fell out. I mean, I almost fell off my chair thinking, holy Christ. I mean, you just dropped everything in terms of what we might get out of this at a given energy potential in terms of 100 or 200 amps and 2,300 Gauss in the magnet strength, where you're measuring things still in dyne centimeters for a single pass of conduit. To me, that's like, okay, there goes the race, boys. But hopefully, with other modifications, like I was mentioning, we may be able to rather overcome that.
Word, man. I'm looking forward to it. Make yourself a little toroid motor, dude.
Yeah, maybe a
Brittlestone.
couple. A
Get
little
that
bit of
thing
time in
spinning.
the 3D department and a little bit of time in the lab, hooking it up to the scope and shit.
Imagine being able to make it and then having you know how they do maglev trains, like have maglev bearings
yeah.
on the z-axis in order to float it so there's no friction, so you can get that thing spinning like ridiculously fast because it wouldn't have
Yeah,
to have
that's why I had a problem with the 2.5 minute video too, is that he's spinning the conduit. It's like, what are you thinking, buddy? The magnets are right there. It's its own subsystem, completely isolated from everything else. Why wouldn't you put the bearings on that part? Why would you not?
But do you see my point? Like with precision engineering, right? With precision engineering and extremely high conductivity materials and a maglev system floated, you could gain like immense efficiency on a motor like this. Uh, I mean, I feel like it would be very, very useful to make motors like this, but it's like the mainstream doesn't even accept it's being a thing.
Well, that's because we live in a capitalist system and people look at cost efficiency. And what we've got going right now in buck per, torque unit is it's not even a comparison at this point. Using all this unobtainium in order to produce some better efficiency is not world practical. Like it's a crass term. I think it's an inarticulate term, but hopefully it gets the point across that nobody in the business quote of making motors and supplying them to other people who need motors to produce their technology are going to be interested in even going down that road because of the cost barrier.
Yeah. Well, I mean, in his setup, they had the most simple way, one single loop of 2 bars. But if you were to precision engineer it and just imagine like doing the whole flower petal thing with as many strands as possible, same toroidal configuration, just adding more vertical bars, right? As many as you could
Yep.
possibly fit, to where it was near approximated as a like a continuous toroid instead of strands, just a ton of strands.
Did you
Then
guys catch his use of 12 gauge wire for the 2I part of the conduit? Like 12 gauge, that's like what you're already running to move 1500 watts of AC to your appliances. You know what I mean? That's an insane amount of power handleability for such a teeny little motor. It's mystifying.
well, it's getting minimizing his resistance. I mean, there's nothing wrong with using it.
But his conduit path is a foot long. Who cares about the resistance piece? Oh, come on, man, get practical.
Well, sure. I mean, I'm personally a fan of oversizing wires. It doesn't hurt anything, and
Oh,
other
no, you
than
got my
all
vote there. I like to over design, but again, holy moly, that is overkill in this design.
maybe he just used what he had laying around. I mean, he was also using plastic straws and stuff in the peasant's method. I mean,
Yeah, that was very high tech. I liked that part. All the straw epoxy and stuff. That's totally my history right there, man. That was fun to read.
but if you were to do the many strands version of the toroid on the inside, you could probably design it in such a way that you could presume the leakage to be extremely close to zero, right? Um, and then, right, if you designed it in that way, where you can presume the leakage to be extremely close to zero, for any gap between the toroid and the ring outside that's not, basically a contact, as long as there's, you got a couple centimeters there or something, you would be safe to assume that the fields aren't crossing, and then you could see if it works still.
Totally. With respect to the conduit itself, in my head, two things came across. One, I was roughly trying to mentally picture just how thin a gauge of magnet wire I would use in construction of the multi-pass conduit scenario. But on top of that, towards the Bedini end of town, I also have some 7-conductor Litz wire. And I'm really interested in seeing how that may affect torque production, even across a single pass.
I do
like
think
to actually
though-
wire them, the 7 of them end to end in series. You know what I mean? That you come in to wire A out of 7, comes out, and you bring it back to wire B, out C, et cetera, all the way through to F, and then finally out the other side, back to the battery. That could actually happen all along one physical path at the block line, and see what that does to torque too. You know, for sake of spatial efficiency in your design, that could be a very significant factor, upgrade, so to speak.
Yeah, this makes me interested in this motor design. I think
I'm hoping more people pick up the weapon. You lift the finger. I want to see more people spending all of $50 or whatever it takes to get into this. My 3D printer for what, 300, even less now, and a scope you can pick up for $100 maybe, and all the magnets are $40. And I want to see a lot more people lifting the finger, hitting Amazon or whatever it takes, get the materials, and go put it on the bench. This really is not a barrier to entry. The only barrier to entry here is physical laziness.
yeah. I mean, do you? I just think that in all the forms of motors that I can think of, right? If we were to someone was to go all out on this and do the whole like nearly infinite strands method and do a test it in a bunch of configurations of different spacings to find the most ideal one and all that. The only limitation and have a maglev float for the toroid bar. The only limitation once they got it set up and optimized would be whatever they're using for like pulling the mechanical energy out, and that would be pretty much the only point of loss. It would be lossless except for at the juncture of where the energy gets pulled out, right? So if they had it like
Yeah.
if they had it because since it would be magleved, it wouldn't be directly connected to like an axle or anything. Basically the rotation of it itself, they would have to have some kind of way to transfer that rotation into into energy that would then be converted to mechanical. But I mean that's a lot less. Whatever loss you get there, you only have 1 point of loss as opposed to however many points of losses in most mechanical systems. I just don't
I
see
do
it.
agree. Yeah, it is definitely a more efficient move to magnetically float the bearings, and so that you're really only looking at a single inefficiency in terms of heat production of the conduit itself, in terms of energy loss. It's the only one remaining that I can think of. And yeah, it's all going to turn into rotational force, torque, coming off of the quote unquote rotor. And hopefully people make the choice, regardless of whether one makes it spin faster than the other, that they pick the obvious choice to spin the magnet instead of the conduit.
Yeah, I just I just wonder like what I'm thinking about the reason why this hasn't been picked up, right? I think that the only reason that they would have to not pick it up, logically speaking, would be that they would look at the explanations that were offered for it as being a field, and in their paradigm, a field doesn't physically exist. And if they accept that as the explanation based on the math, because they love math, then they'd be like, "Oh, physical A field, nope, big nope, nope, definite big nope," and then they never go near it and don't touch it.
Precisely. I think the barrier for entry on the academician side is the academician.
But that would mean that they've like artificially kept this from becoming a motor design because of the implications that it would carry.
And incorrect analysis when they have no respect for the empirical entirely. And that's a common theme, isn't it?
Well, sure. But I'm just saying, like, that would mean that, like, because we know that, the motor works, therefore it's pretty safe to assume that it has been in some way artificially suppressed. So, what reason would they have had for it? It must mean that they presumed that the A thing was the correct interpretation. Doesn't mean that they're right. It just means that that's what they assumed, and that's why they suppressed it. So, whoever did that must have seen that as a threat to their paradigm. That's probably why they threw Marinov out a window.
Yep, could be.
Because he got like thrown out of a window, right?
No, everybody in the capitalist system hates competition, and that's just what humans do, man. That should never be a detriment. It should never stop people from making the decision to better their lives, technologically speaking. Who cares what other people are doing to other people? It's what you're doing for yourself, and what you're doing for other people that should be far more relevant in your decision making.
Well, thanks for the talk, and it's been a good reading night, guys.
Yeah, it's been a hoot.
Yeah, that's a good conversations, man.
All right. With that said,
Any other questions from the gang?
No,
We got
nothing here.
20
Thanks again, Stone.
20 people here. No other questions. Alrighty then. Good enough for me. Good enough for you.
dude, much appreciated, Stone. Went hard on that analysis, dude. You were like, dude, I just
Super
spent 3
hard.
hours on this.
Dude, you did a PhD level breakdown analysis.
Dude, that was awesome.
And then you guys were like, I'm gonna cancel it. He was like, what? That makes sense. Now I get
Yep.
it.
No, we did.
Very good. Very good.
We had everybody in the house, dude. Dr. Bennett came through. Stone came through.
Yeah, it was
Toby ended
peaking.
up coming.
Speaking of
Yeah,
Toby,
this might have been my favorite reading night so far.
I
heard
learned a lot about the freaking Maxwell and Hertz equations from Bennett. Like, I didn't realize that they had this setup of this real magnetic field and this real electric field and this non-real vector potential component that's used to produce the field, but it's not real. Like, I didn't realize. I never
Sorry, I
realized.
thought that was coffee, really.
No worries. I never realized that was like a thing in their paradigm. That's wild to me. 'Cause they're like mixing and matching real and non-real components within the same set of equations.
Don't forget to verify everything you've heard.
Yeah, I asked ChatGPT. I haven't gone to like Maxwell's book to look at it, but
Man, why would you talk to a Cocker Spaniel about such a thing? My God. You know what I mean by that, right?
well, B equals nabla cross A is a real equation. Like that's the definition of that's the relation between B and A.
No, but you know what I meant when I said that, right?
Yeah, you're making the ChatGPT the Cocker Spaniel.
That they have roughly the same level of actual intelligence. Yeah.
But Cocker Spaniels are cute.
all right, I'm about to go do outro. Peace, y'all.
Yep.
All right, guys, make sure you buy copious amounts of Brushtail coffee. If you're not buying Brushtail coffee, you're basically not a cool person. All right, see you guys tomorrow for Flat Earth Friday. Thanks for everyone for coming out for research and reading night.